Okay, well, we have heard on quantum theory already quite a bit, and also on theology. You notice that in my title I left theological, and the word theological I left it out. It's not completely by accident, because I'm not sure which one of the implications are theological. So I have no claims of being a theologian at all. Let's see whether this works. So the main questions I would like to discuss is first the differences between classical quantum physics. Just it will be rehearsal for most of you because that's well known, but also that list will certainly not be complete. So I will make a selection of what I think the most significant differences in this context. And then of course also the question whether these differences have theological consequences, whether quantum physics has problems of its own in the domain of religion and faith, or maybe that problems that exist in the description of classical physics may disappear, may be solved in the quantum context. But I'm not only interested in theological consequences, but also in the consequences for our view of man, so say anthropological consequences. The view of classical physics I would like to defend here is, which is very close to what has been stated also by other people, is that the state of a system in classical physics is just identical to the specifications of the values of the physical quantities. If you know that you have to specify the values of the physical quantities to specify the state of a system. That is more or less synonymous. Also what is self-evident in the classical context is that a measurement determines the value of a quantity, and also that value is believed to exist independent of the measurement. So the measurement determines the state of affairs in the system. Realism. Second point is that events take place independent of the question whether they are observed or not, independent of the observer. That is what I name objectivity. And then finally that the future state of a closed system, of a classical physical system, is completely determined by its present state. And that is determinism. So in that sense, there is no future, no separate future for a classical system. The present state of the system contains the future as well as the past, we should say. All this is, so as a prototype, I take here a classical mechanical system. So the objects move under the influence basically of Newton's second law. So if you know the law, if you know the force as a function of time, and you know as the initial state, the position and the velocity, the future is fixed. That's true for a system of a single mechanical particle, it's true for a system of any number of particles. But it's not only true for mechanical systems, the same holds also for radiation, for systems composed of charged particles coupled to radiation. So Maxwell's equations combined with Newton's equation basically determine everything. And this kind of system obeys has the properties that I just mentioned of objectivity, of realism, and of determinism. So, in fact, the picture of the world as a classical physical system is, well, can be viewed as a clockwork. That's in fact also what has been used in history. So, in theological picture, you could say that also is very suggestive of viewing, if you see nature as creation, the creator is some sort of clockmaker, which of course suggests a deistic picture that the initial state immediately after the creation is sufficient to determine the future. After that, there's no room, in a way, within the physical picture for intervention. But of course, this picture is not without problems. It is only a picture. It may or may not be the truth. But if the future is determined by the present state of affairs, that is, then you can first ask the question how you still can believe in the possibility that God acts, that God does something, that God interferes. There's no room for that in the description itself, unless you believe that by God acting, that leads automatically to breaking the laws. violation of laws, and that is, well, some people think that is typical of God, that he has the power of breaking laws. On the other hand, also for theological reasons you could defend the thesis that this is not in God's spirit to break laws, that is more in the spirit of man. But it's not only for the acts of God, it's only for our own acts. If we believe, as we experience, that we have freedom of choice in the things we do, then it is not quite easy to combine that with this classical picture in its deterministic aspect. How can we have freedom if the state of affairs of all material particles, including ourselves, that also determines what is going to happen? That what seems to suggest that our freedom of choice must be an illusion. You can go further. You can ask what we have done already yesterday evening. What is the basis of our consciousness, of the existence of our mind? How can there be room for that if we have the materialistic picture that our consciousness, our mind, our free will are basically byproducts of material complexity? That is I think the basic scientific view on life, and including man. And even more profound, at least in my mind, if we also our thinking is viewed in that way, not only our consciousness, but if our thinking is only viewed as a material process of the brain and the nervous system, it's neurological and firing of neurons and that kind of things, then our thinking is a natural phenomenon, just as the wind blowing over the water and giving ripples. And the ripple doesn't tell us anything. The ripple has no claim of being true or false, it's just there. So how can you have these qualitative differences, that our thinking also not only is a neurological process, but also refers to something, refers to ideas, refers to concept out there in the world. So in short, how can we adhere the concept of truth or falsehood to our thinking if we believe that our thinking in the picture of classical physics of the world as a material system, if our thinking is just a byproduct of the material complexity and the processes in our brain. Now, quantum mechanics has suggested a different picture of the world. It did not arise for philosophical reasons, not at all for the problems that I just mentioned, but it solved numbers of problems in physics. And just to name a few, also it has been named before, the first, it started, say, with the ideas of Planck, Max Planck, on the spectrum of black body radiation, where the quantum hypothesis led to the spectrum of dark radiation. And that was basically the birth of quantum mechanics in 1900. But also the structure and the stability of atoms and molecules, based on the picture that arose of atoms consisting of a nucleus and electrons, and molecules consisting of atoms. They have a stable structure, and to understand that structure it is essential to have a quantum mechanical description. Classical physics will not give the description that works. So quantum mechanics simply was born out of physics and not out of philosophy. What quantum mechanics also does is that it explains the properties of matter in terms of the constitutive building blocks. Classical physics on the microscopic level works fine, as we all know, but to explain why matter has the properties it has, like the color of materials, whether a certain substance is a liquid or a solid, all that kind of questions can be understood also on the basis of, say, the structure of matters on an atomic or molecular level. So that also requires quantum mechanics. And another example is to understand how the sun can continuously produce energy as a nuclear process, nuclear fusion. That's also, of course, requires quantum mechanics. Now, quantum mechanics brought in new aspects, as we all know. It started actually for light, the shock of quantum mechanics in the theory of light was first that it was not just an electromagnetic wave, as followed from the theory of Maxwell. But light has a grainy structure. It has a particle structure. It started with Planck, and it was made more precise by Einstein in his quantum hypothesis, with earned him the Nobel Prize. That light contains smallest energy particles, so that brought in the duality of light, which was just understood by the experiments of the 19th century of Young and Fizeau and Fresnel, that light is a wave, but it also contained a particle structure. Opposite to that, complementary to that, you could say, in the word of Bohr, that material particles, which we know matter was known to have a grainy structure. It contains atoms as smallest building blocks, as particles, but also particles that started with electrons, the lightest particles known, that they can display wave aspects. Light can also wave particles can, just as light, display properties as frequency, wavelength. It can give rise to interference, which can be explained only if you have this wave picture of some sort of structure that is not localized. And that was introduced by Du Bois in the early 20s of the 20th century. So that's where you can say that the distinction in classical physics between radiation on one hand and matter on the other hand, that's the two types of physical objects that was lost, that distinction. Both matter and light have aspects that refer to particles and to waves. So that also implies that we had the two basic theories in classical physics, Maxwell's theory for radiation, for electromagnetism, and Newton's theory for classical mechanics. They merged into one. Quantum physics describes both in a single theory. The basic equation of motion is then the famous Schrödinger equation that we know here. This is Schrödinger himself. So the way that the state is described, as also has been mentioned, is in a much more abstract way than in classical physics. In classical physics, you just give the values of the quantities, and then you know what the state of the system is. But in quantum mechanics, the state of the system is something abstract, a state vector in a multi-dimensional state space. For one particle, it is the wave function. It's usually referred to as psi for mystical reasons, I understand. Now, the laws of motion is just a single equation, actually. It's Schrödinger's equation that holds both for material particles, for electrons, but also for radiation fields. There's no separation there. Well, in quantum field theory, it is a little expanded, but the basic ideas remain the same. Some other new things that arose in quantum mechanics is the famous uncertainty relations, that there are pairs of quantities that cannot attain a precise value both at the same time. Velocity and position is one famous example, but there are many more. So the uncertainty relations show that once if you know everything there is to know about the state, not every quantity is precisely defined. The second aspect is that there is an enormous distance between the observable properties of a system, say the things you can measure in an experiment, and the structure of the theory. The theory has a very abstract mathematical structure, and it contains concepts of which it's not so easy to say whether they exist or not, whether they are part of reality. It's much more complex. So the theory, it also took several decades to be developed in this mathematical structure. If you know the state vector, so if you know everything there is to know on a quantum mechanical state, then even then the results of a measurement are not precisely determined. There's indeterminacy contained in there. It has, so the quantum mechanics, the quantum physics is inherently probabilistic. So that is it's a probabilistic theory. That is also an aspect that I consider crucial for the effect on the world, on the picture of the world that quantum mechanics has given us. And finally, that is maybe the most profound, at least that's what I want to stress, that even when you know everything about the state, then you are not certain what the values of the observable quantities are. So if you do a measurement, something comes out, but you cannot say that that property existed already before the measurement. So then you can ask yourself the question, what are we doing when we do a measurement? It produces a result, but if that result does not reflect the property of the system, then what have we done? So the whole idea of reality itself becomes problematic. So these are, of course, all well-known features of quantum mechanics, but I gave you just a list of what I consider to be distinctive also in the context of our view of the world, our view of life, of man, and maybe also our view of creation. Okay, one example I want to briefly discuss is the interference experiment for particles, so the experiment of Young. You have here two slits in the screen. There's particles coming in, say electrons, and then all physicists in the audience know this experiment, of course, that you get an interference pattern on the screen, and the interference pattern, to describe it, requires a wave description of these particles that's coming. Interference patterns can only be understood as a cooperation of the waves through slit 1 and through slit 2. It's a cooperation between both. And this effect happens for light, well, that is basically the original experiment of Young, but it also holds for electrons, and the effect for all particles in principle. Now, you can ask yourself the question, how is that possible? How can particles interfere? And a related question is, what is the wave? What is waving there? And what is oscillating? That is a question that is not so easy to answer. Well, the first interpretation is simply saying that, okay, you have particles coming through slit 1, particles through slit 2. So here, particles coming through slit 1 and through slit 2, and they collaborate. These particles collaborate with that particles to produce the interference pattern. Now that interpretation turns out to be wrong. It's very easy to test. If you make the wave weaker and weaker, and you take a longer time for the experiment, you get exactly the same pattern. If only one particle at a time is in this experiment, you get exactly the same result. So a particle does not need another particle to interfere. The particle interferes only with itself, as Nienhuis used to say. So then, does that also mean that the particle passes two slits? Well, for that you can look at also experimentally. You can put a detector here and you put a detector there, and then see what happens. And then it's obvious that each particle passes only through one slit, it never divides itself. So, well, in the old interpretations people say, well, that means that the measurement disturbs the particle, but that is not correct, because you can do exactly the same interpretation, get exactly the same result, if you simply when this wave and that wave is completely unchanged. All that has to happen is that this wave is entangled with the detection apparatus here and there, and that the detection apparatus betrays whether slit 1 or slit 2 was passed by the particle. That is enough to make the interference pattern disappear, and that is the price you have to pay for knowing which path the particle went. So which path information destroys the interference pattern. So the particle always passes only one slit, but on the other hand, the fact that two slits are open changes the interference pattern. The particle passes only one slit, at least that's what happens when we detect it, but it still seems to know that whether the other slit is open or not. How can the particle know that? That is one of the miracles of quantum mechanics. So let's discuss this question, this statement, that identical systems in quantum mechanics described by identical state vectors can lead to different measurement outcomes. That is the central statement, I think, of quantum mechanics. And the question is, what causes these differences? Now, okay, there is to this question, there's the wise answer, what I call the wise answer, that's the Einstein, the answer of Einstein and of other people. Simply say, well, there must be something in the system we don't know. How wiser can you be? If you simply say that there's a an unknown cause for an effect that is there. We don't know what it is, so something we don't know must be the cause. But this statement still has consequences. First of all, it means that the different measurement outcomes simply reflect hidden differences in the system itself. That is basically, well, rephrasing this answer. It also means that quantum probability, the probability aspect of quantum mechanics, is the result of uncertainty. That there are things that we do not know, and that we could have known, or that maybe that the system knows, or maybe that God knows. Who knows? It also means that quantum mechanics itself is incomplete, because there are hidden aspects in the system that are not described by the quantum mechanical state factor, which is all that quantum mechanics can provide. This is the situation that Einstein has tried to defend, and also Schrödinger and de Broglie and Bohm, all kinds of people in the early days of quantum mechanics believe that this must be the case, that there must be something hidden in the system. So here are these old champions of the model of hidden variables. Okay, now let's look at to see what happens in quantum mechanics when we have a system that consists of two separate systems, of two subsystems. I want to go to the aspect of entanglement that has not been discussed very much yet at this meeting. Well, it has been mentioned, and of course everybody knows what it is. So we consider now a quantum system that consists of two parts, and they are spatially separated. That's indicated by this bar. They can be far apart. So we have the systems A and B, and well, what is typical of quantum mechanics is the linear superposition. So we can have a state psi A and phi B for A and B, which we can also have a state phi A prime and phi B, psi A prime and phi B prime. But when that is possible, quantum mechanics tells us that you can also have a linear superposition of the two, something in between, you can say. But both of these states are present for the system. Now, it is also typical of quantum mechanics that if you measure an observable, then you change the state. Then you end up in an eigenstate. Now, when you have a measurement of an observable only of system A, with this kind of system, then the state changes after the measurement. But in this case of this entangled state, then also the measurement on A changes the state both of A and B. And that's remarkable because you do a measure, you have this state, you have this physical situation of A and B. Something is done on A measurement. Suppose that there's someone here who has the system B in his hands, so nothing can happen there because no one touches it except the state is simply there. And still, the state vector that describes the state of the system changes. So that raises questions on what is the significance of the state vector. Now, let me just briefly summarize the famous Bell's inequalities because they are important for my argument, but I don't want to, well, those of you who know it, because they need an explanation, and those who do not know it, maybe I use a metaphor to explain what Bell's inequalities tell us. So we have here a specific state for two spins. Spins of a spin is an internal aspect of particles, such as electrons. The spin is an angular momentum that can have a direction, and it's typical for the spin of an electron that for any direction it can have only two values, which we go up and down, and indicated by an arrow up or an arrow down. So here I have two of those spins, the A and B. I have the state where spin A is up, spin B is down, or I have the state that A is down and B is up. And I have a linear combination of two. That is the state that can be prepared for either two electrons or even for two photons. And in this state, in this specific state, it has the remarkable property that if I take a given direction, because you can measure this spin in any direction. Now, if I take a direction in space like this, so I measure whether it's that way or that way, then it turns out that when B is up, A is down in that same direction. And that is true for any direction. So there's a complete anti-correlation between these spin directions. Now, there are two logical consequences, because this means that if I measure, B, the spin of B in a specific direction, I get the result. And since I know that in the direction of A, always the spin is completely opposite. So when I measure B for the same direction, I also know A without touching it. I don't touch A, I only measure something on B. So that also means that we can simultaneously measure the spin A in the direction U or in a different direction. That they can go at the same time, because one of them can be measured by touching B. So I do one measurement on B in U, and I measure A in V, and then I know A in two different directions. And this has very strange consequences, because such a measurement basically cannot be done directly. It's forbidden by quantum mechanics, because the states of the spin in U and the spin in V are incompatible. They cannot be observed at the same time. They don't even have a specific value at the same time. Now, let me, to see what Bell's inequalities say, let me use a metaphor. So I represent a spin as a house. For each spin, I need three directions in which I measure the spin, for each of them, both of A and B. So I have two houses, A and B, and each house has three windows. A window represents the spin in a given direction. It can have two states, up or down, which I call for the window open or closed. And that, since quantum mechanics allows us to measure the spin in one direction only, that means that this is a very peculiar house, because we can see only one window at a time. When we watch one window, the other two windows of the same house are covered. They cannot be seen. So here are the two houses. We have the house A with window 1, 2, 3, so the 3 floors, and it's the same for B. And each window can be open or closed, but only one window of A and also one window of B can be seen at a time. So it can be A1 and B1, or A1 and B3, but only one in each. And that's the rule of the game. It's imposed by quantum mechanics. Now, in a given state, the state that they have specified, quantum mechanics predicts that whenever A1 is so A1 is a window, when A1 is closed, B1 must be open. So here, when this window is closed, that window must be open. And when this is open, that one must be closed. That's the complete anti-correlation. And that's true for each three of those pairs. So that means that, for instance, we can observe A1, so that's the window in house A on the ground floor, and B2, which is the first floor, or do you call it the second? But at least the second level of the house for B. Then you know the state both of A1 and of A2. Because B2, when it's open, I know that E2 is closed. Anti-correlation. So then you can measure the probability, simply by repeating the measurement, that A1 and A2 are both closed. Now, logically speaking, when A1 and A2 is closed, A3 can be either closed or open. So this probability that A1 is closed and A2 is closed must be identical to the sum of the probabilities that A1, A2 and A3 are closed, or the probability that A1 and A2 are closed and A3 is open. Because here I assume that A3 is either closed or open. So here I use this logical two-value test. I exclude the third possibility that you have been discussing. I think this is, the topos will be very useful to discuss here. That's all. Yes. But if I follow this logical argument that when something is true, its opposite must be false, then you can also conclude from here that this probability, that A1 is closed, A2 is closed, and A3 is closed, that must be smaller than the probability that A1 is closed and A3 is closed. For obvious reasons, because I lost one condition, A2. And this last one, the probability that A1 is closed, A2 is closed, and A3 is open, that must be smaller than the probability that A2 is closed and A3 is open, because I forgot the condition on A1. Yeah. So that is a very logical result, simply by using this argument that when something is not true, it must be false. Now, it turns out Bell's inequalities simply show that there are situations that this is that this expectation that this must be smaller than the sum of their two, that is violated. That can be wrong. There are cases when this is simply not true. So in this metaphor, I think it is clear that this is in a way shocking, but also it shows also what the presuppositions have been, what we have, which hypotheses we have made. Now this is an example of Bell's inequalities, and for a proper choice of the three spin directions, this inequality can be violated. What are the assumptions that we have made here? Well, they have already been discussed in a very elegant, detailed way by a paper with Einstein as the first author, the famous Einstein-Podolsky-Rosen paper of 35. Since they say that since AU, say the spin of the direction of spin 1, can be determined by observing BU, that also means that in that case, because I can determine what AU is without touching A, then it's very logical to also to assume that AU exists, that it has a precise value also when I do not do the measurement. And that is realism in a simple way, that a quantity has a property even when I do not measure it. That is well, the simplest expression for realism that I can think of. But also, you assume that if I do a measurement on B, then you cannot change the value of any one of the AUs, of the spin of A in any direction. Because if I do something here that can have no effect on another part of my laboratory, or another part of the world, or another part of the universe. In quantum mechanics, in fact, the effect of the change of the state vector occurs instantaneously, or however large the separation is. So that since these are the two hypotheses that have been made in this argument, the conclusion must be, since the result turns out to be wrong by experiment, and also by the prediction of quantum mechanics, so quantum mechanics is confirmed, it means that one of these assumptions must be wrong. Now, the state of affairs is, I think it's fair to say that most physicists give up realism. So they drop the first statement in order that they can maintain the second one. So that also means that, well, the first statement corresponds to what I call the wise answer. This answer, that the cause of the differences in the measurement outcome for identical systems and identical states, that there's something we do not know. There cannot be something we do not know. So that means that we come to the answer that is not the wise answer, it's the Copenhagen answer. So then the answer is simply, there is nothing that causes these effects. So that is, in a way, this is a completely different answer than the answer of something hidden. There can be no cause for this effect. So here, if you look at this statement of quantum mechanics, that identical systems described by identical state vectors lead to different measurement outcomes, for that effect there is no cause. That is the simplest way I think you can formulate this result. Then you can say that the probability does not arise from uncertainty. In the sense, there is nothing we do not know when we know the state vector. We know everything there is to know. That also means that the system itself does not know what the measurement outcome will be before the measurement has been done. And if I believe John Polkinghorne, if he says that if God knows everything, he can only know everything that there is to know. Here is nothing to know. So even God does not know what the measurement outcome will be before the measurement has been done. That seems to be a theological consequence of probability. And also the outcome of a measurement remains undetermined, not only uncertain, but simply undetermined up to the instant of the measurement. It also means that the outcome of a measurement does not reflect the property of the system. It does not reflect the property that the system had before I do the measurement. Because you cannot call this outcome a property, but that property could also have been something else for the same state. So this is still a dramatic consequence of the simple known facts of quantum mechanics. So this is Bohr and Heisenberg were the first champions of this Copenhagen statement. But there are other possibilities that I would like to, which are less well known than Bell's inequalities. But this is also very interesting to find if you're familiar with quantum mechanics, which most of you do. It's very easy to find the state for two spins 1/2, say, if you do spins. That whenever in the language of the windows, whenever the window 1 is closed of A, then also B2 is closed. You can make such a state that always when A1 is closed, B2 is also closed. The same state also has the property whenever B1 is closed, also A2 is closed. Yeah. So when the ground floor of A is closed, the first floor of B is closed, and when the ground floor of B is closed, the first floor of A is closed. Also, it can be true that sometimes in this state you observe that both ground state windows are closed. Both A1 and B1 are closed. And still, it never occurs that on the second floor both windows are closed. You can easily construct such a state. So here there's not an inequality that is violated, it's just one logical statement that turns out not to be true. So this is called Hardy's impossibility, and it is a very simple exercise in elementary quantum mechanics to construct this state. And you see what the probability are. It's about 17% of the cases that this will happen. So here I repeat that statement. So here you see, I can see only one window at a time. Well, whenever when this is closed, always B2 is also closed. Whenever B1 is closed, always A2 is closed. So I have now two houses only with two windows. The third window doesn't enter here. Sometimes both A1 and B2 are closed, and B1 are closed. So the ground floor windows are both closed. You know when this is closed, also that one must be closed, the one I cannot see. And when this is closed, also A2 must be closed, but it never occurs that A2 and B2 are both closed. But this is really, whenever I see this, it makes me some sort of excited because there's something wrong. This cannot be true. It is. Well, there are statements on quantum mechanics by many of the pioneers which are interesting also to give because they have some philosophical implications. They have done on several occasions, but it's interesting to go over them because they view also how differently the founders of quantum mechanics, who agree on the structure of the theory, but still they have a completely different view of the interpretation of that. Bohr says, for instance, there is no quantum world. It is wrong to think that the task of physics is to find out how nature is. Physics is concerned what we can say about nature. That is a typical Bohr statement that it's useless to make statements on things that we do not observe. So we do not make ontological statements, only statements of outcomes of measurements. It sounds very pragmatic. And Heisenberg says something that is related on the world, that the atoms or the elementary particles, so systems that obey quantum mechanics, they are not real. They form a world of potentialities or possibilities rather than one of things and facts. So this also undermines, of course, the realistic view that the concepts that occur in the theory, or in physics, like atoms, and there are hardly any more fundamental concept than those, that they are not real, and that is what Heisenberg has stated. The idea of quantum jumps, I haven't gone into that, but we know that also quantum mechanical systems, in quantum mechanical systems many observables have discrete values. So they can, for instance, the energy level of an atom, it can have certain values, and the values in between are forbidden. And still, an electron in an atom can go from one energy level to another one. And that raises the question, how can an electron go from one energy value to a different energy value without passing the values in between, because they are forbidden. And the answer of Bohr was there are quantum jumps. It jumps from one to the other. Well, I don't think that's an explanation, but at least you give a name to something you don't understand. That is what science does very often, actually. But Schrödinger didn't like that at all, and even 20 years later, in the 50s, I think, when Schrödinger was getting quite old, that he didn't like this whole idea of jumps at all. He said, if you're going to stick to this damn quantum jumping, then I regret that I ever had anything to do with quantum mechanics. Schrödinger. the main giver of the basic equation of quantum mechanics. Observation, there's Jordan who said that observations not only disturb what has to be measured, because that was the old interpretation of the uncertainty relation, that the measurement disturbs the state and thereby creates uncertainty. But that turns out not to be the correct statement. Observations do not disturb the measurement, but simply observations produce the measurement outcome. In a measurement of position, the electron is forced to a decision. Previously it was neither here nor there. So that is also undermining the idea of realism, that an electron doesn't need to have a position until someone asks the electron what the position is. Before that, the electron doesn't have to know itself where it is. It is Mermin who said that precisely, that is a much more recent statement, that precisely how the particular result of an individual measurement is obtained, the transition from the possible to the actual, that was the phrase of Heisenberg, that is inherently unknowable. So that this change in the measurement from the potentiality of what the measurement outcome can be to one actual value that will be produced, that process cannot be known. That is what Mermin said. It is, well, on the other hand, a measurement is something very fundamental within physics. So if you have something that is so crucial to determining anything in physics that you cannot know what happens there, that is shocking. Rosenfeld, who said the human observer whom we have been at pains to keep out of the picture seems irresistibly to include into it. This refers to the fact that an observation is done by a human observer. Until the moment that there's someone to notice what the measurement outcome is, the state vector is unchanged, in the sense that the best information, the best description of the state is the state vector. Only after the measurement result is known, then the state is changed, and you go to the state corresponding to that measurement outcome. But there, in a way, it seems to depend on the human observer who observes the measurement. So in a way, some people have also suggested that it is consciousness here that enters into the picture. I don't think that's completely true, but that's, at least this was Rosenfeld said here. Understanding, and that is maybe the most amusing statement that made by Rachel Feynman, that it is safe to say that no one understands quantum mechanics. It is what Feynman said in the 60s. So it's, and in fact, basically, the state of affairs has not fundamentally changed since. Okay, now what can we conclude from all this? So these are my observations. I have been thinking about the implications of the well-known structure of quantum mechanics. Now, in my mind, I think that the classical picture, the picture of a deterministic world, as we have in classical physics, that is material, that the world consists of material particles that are deterministic and also autonomous, that behave and that take their own decisions, that everything else depends on that. So that creates problems on the source of our consciousness. Consciousness in the sense that we do not conceive ourselves just as a complex living system, but also we experience things in our minds. We do not just behave. At least I know of myself that I also have an inner life, and I suspect for most of you that that's also the case. Because we have some sort of familiarity. But it's very difficult to prove, apart from your own inner experience. So consciousness is not quite obvious in the context of classical physics. Also of meaning. What is the meaning of life? What is the point of the things we do? How can we explain the fact that we experience the free will, that if we take a decision we could also have done something else? Although we never do, we only do one thing at a time, but still we believe, and also we call each other responsible for the actions we take, as if we could have behaved differently. It also, you can ask the same questions for actions of God. In the classical world, it is not so trivial to have the idea that how God acts, as we have been seeing. Well, in the quantum physical world, things change, but not so dramatically as some people suggest. I think determinism is modified. I don't think it completely disappears, because Schrödinger's equation still describes in a deterministic way the evolution of the wave vector, the state vector of a system. Although the state vector itself does not determine what is observed. Also, the concept of objectivity is modified, and the realistic view of nature, that the outcome of a measurement reflects a property of the system, that has to be given up. But what is not given up is the materialistic picture of the world. The world is still a world of matter. And so it has been suggested that maybe our consciousness and our free will are products of the quantum indeterminacy, that within the room that is left by the quantum state vector for taking decisions, that is our freedom. I'm not convinced that that can be true, for the simple reason that it is a different kind of mathematics that you use there. You use probability theory, but still the distribution of possible outcomes is still completely fixed, also in quantum mechanics. So determinism is modified, but there is still a hidden determinism in the probability statements that can be made. And if we have to defend our free will simply by saying that we have to do a lottery to determine what we can do, that is not what I think that free will can be. So there have been suggestions that quantum mechanics leaves room for the things that have been eradicated by classical physics, but I'm not convinced that is really true. Quantum physics is essential for the molecular structure of, as the material basis of life. So in a way our lives depend on the validity of quantum mechanics. Even a simple aspect is the Pauli exclusion principle is essential for the fact that atoms, when you add electrons to atoms, that they have this periodic structure that we know from the periodic table. And if the Pauli exclusion principle would not hold, all the electrons would go to the ground state, and all the atoms would probably practically be the same, and all matter would collapse, and we would not sit here. The effects of entanglement, they do not seem, they are dramatic effects in quantum mechanics. They are now used in quantum information and quantum communication, and they are ideals for basing quantum computation on that. Now, I do not believe that can explain very much on the level of where our existence depends on, say, the structures of life, for the simple reason that the structure of molecules depends in an essential way on quantum mechanics, but not so much on entanglement. So entanglement is a very special aspect of quantum mechanics, and that is confirmed by experiments. But I do not think that our neurological or brain processes can be explained better if we take entanglement into account. So you see that I'm a little bit skeptic about the idea that quantum mechanics may really give new probabilities, new properties, and new possibilities that classical physics did not have for explaining the world we live in. We have seen, that is a list of conclusions that I would like to conclude with, quantum mechanics shows that the scientific world picture is stranger than we thought. That is certainly true, and also there's no reason to believe that we are at the end of it. Physics will have more surprises when we continue the research. So I would say that it is very miraculous that quantum physics works well as a description of the physical world. There are lots of discussions on the interpretation of quantum mechanics, but there are no discussions on how quantum mechanics should be used to make predictions. So it works very well. There is no fight there. It's only, as I showed in these statements by various physicists, people phrase and explain things in a different way, but it has no bearing on the results that quantum mechanics produces say, for explaining things and for doing measurement. It's just the interpretation that is different. So you could say quantum mechanics can be used without interpretation. Quantum mechanics does not need an interpretation. The merit of quantum physics to me is mainly that it makes us a little more modest. That that there are many things that we can use, and it is a miracle that we can. That science turns out to be so powerful a gift that we can describe the world, that we can give a correspondence between our predictions and the outcomes of a measurement without really understanding it. So that I think that is the best lesson that I think we should go from that, is that we should be a little modest in making universal claims on the basis of the science that we know, because apparently we can, even when we know things, when we can use things, we do not have to understand them. So that is basically what I wanted to say, and whether this also has theological implications. Well, I've indicated a few. I think that maybe modesty is hardly a theological statement, I would say. But still, I think it is an important lesson from the power that physics has given us, that still we can do more than we actually ourselves understand. Thank you very much.
Thank you very much indeed. Good. Well, we've again got some good time for questions and discussion. Who wants to kick off? Yes.
I wondered if we had learnt about our world from the quantum mechanical end first, and the things that we, so to speak, don't understand, but we can use it to predict, what might our ideas be on the matter of determinism and subjectivity, or objectivity and so on, that the classical picture gave us? In other words, if we came from the bottom end up. Have you ever thought of that? Or could you comment?
Yes, I have. Well, of course it is clear that the fact that quantum mechanics is surprising simply indicates that our intuition has been formed by classical experiences, by experience in the context of a classical world. But on the other hand, quantum mechanics exists already for almost a century, and it has been widely studied and also understood as far as it can be understood in its logical context. So I think that we have also learned to modify our intuition in the sense that we can almost experience quantum mechanics and put ourselves in the position of electrons and see how that would be. And that, of course, it's very hard to imagine not knowing where you are, as seem to hold for an electron that goes unobserved. But I think that simply, if I see that not much has been changed since the 30s, when quantum mechanics was for the first time really understood to its practically full content, apart from of course, there has been progress, of course, in quantum field theory, but that is, I think, these funny aspects here were already there in the 30s. So I doubt whether that would have made much difference.
Questions? Yes. Peter.
If I could make one slight comment, it would be that it's important to see that you have a two-particle system when you have these particles. The fault with the realism of Einstein was that he said you've always got one particle and another particle, but the two-particle system nature is very, very important. And then as soon as you measure one of them, you destroy the two-particle system as a system. And after that, you've simply got one particle juxtaposed with another particle, although you know more about their states. And I find that the most helpful way of looking at this system is that the particles are not just living together, they're actually married.
Yeah, okay, but they can be very far apart in that marriage. That is in a way shocking, that this bond between them survives an infinite distance.
It is extremely interesting and fascinating.
Yeah. Okay.
Yes.
I've written down, and now I'm not quite sure if I know what you meant. Did you say that with the quantum theory, it's less deterministic, but it's still materialistic? And by that, is that that's what I've written? That you said,
just repeat that.
yeah, that you were looking at the differences between the quantum and the classical, and you said quantum means that the universe is less deterministic, but it's still materialistic. Do you mean materialistic or it's open?
No, I mean materialistic is at the basis of the world, also in the quantum mechanical description of the world, is just material object. So like matter and say electromagnetic fields. I mean the basic building blocks of the physical world are no different. Only the properties that these building blocks turn out to have, they are modified in the quantum mechanical description. But the world does not bring in a completely different kind of building blocks. That's what I mean. It's if we identify the world as a physical system, and that is basically what physics seems to suggest, because everything that we see, every phenomenon can be described as a physical phenomenon, and there seems to be nothing outside of that. Of course, there the statement that the world is basically a physical system, and that all the higher functions that we experience or observe are simply byproducts from material complexity. That statement can be maintained both in the classical description and in the quantum mechanical description. That's what I mean.
And so when people like John Hawkinghorn, I know it's wrong to put God in the gaps, as they say, but are you then saying exactly the opposite, that there isn't, that there couldn't be the possibility of God in that gap?
Yeah, no, I think I would say the same thing, that there is no, well, if you would use God as an explanation for the things we don't understand, then you use God simply for justifying that there are things we don't understand, but it doesn't explain anything. And that would not be different in the classical or the quantum mechanical description, I would say. But there people hold different views on that. Some people say that the quantum description really gives a completely new picture of the world, where there's more room for the higher functions than, for instance, in indeterminacy. And I doubt that very much.
Just thinking of you touched a little bit on free will and determinism and so forth, so, and I think you rightly pointed out that quantum events would, if they were significant in free will in any real sense of the brain, they would not lead to free will, they would lead to randomness, which is clearly not free will, and therefore that kind of account doesn't work. I suppose the other reflection, just again bringing in the biological angle, is that all the events, the physical correlates in the brain of mental events are all summations, I would have thought, of a very large number of quantum events, that all the things that we generally think of biologically as being significant in terms of describing how a brain works, in terms of synaptic transmission and action potentials and all these various things, they're all kind of things which are actually averaged out quantum events at a much higher level.
Yes.
Mechanisms really, and I don't know if anyone has any reflections or thoughts of whether there are any quantum events per se that would actually make any difference, except when they're all averaged out to something that would be a law of averages, which is what biologists talk about, laws of averages really, when it comes to these sort of mechanisms. So,
my personal first order statement would be that in most cases an average over many quantum effects leads to the validity of a classical description. It's not always the case. There are also macroscopic quantum mechanical effects, like in superconductivity and that kind of things, where you have a large degree of cooperation between the various elements. But what is typical for any living system is that it contains many elements of a completely different nature, not identical, not identical elements like you have these quantum physical effects. So I would not be very convinced by the idea that the quantum effects also in living systems are important simply because you view the brain as composed of a large number of quantum mechanical elements, but maybe someone else has different ideas.
Well, I think the one that plays in the physical sciences that people are first looking for evidence of entanglement in a biological system is in photosynthesis. As far as I know, they've not yet found it and may never. But I think a lot of people coming in from the physics end think that if you're going to find it anywhere, that might be the first place that you'd find it.
Simply because it's very accessible to investigation, not so much because that would be the only case where it would work. It's simply that has been very broadly studied, so that we can hope that that can be understood fully.
I wondered, can I just finish off just to come back to what I was saying?
Okay, yes.
Just to say, so if we know we have free will, if classical mechanics can't explain it, and you're saying quantum mechanics can't explain it, is there ever going to be something which will explain it, or are we going to cover it without?
That's in fact, in psychology now there are quite a few of people who simply investigate how the free will works, how it correlates with the observable actions of the brain. If their conclusion is not, as you say, that we know we have free will and we try to explain it, if a experiment proves that free will is an illusion. That's simply a different attitude, that you take the material basis that we know as more absolute than our inner experiences. And that is, I think, a very important choice, which now is made more and more. I think that is a moment of choice that I think is very important, because I would say that if we do not take our experiences seriously, we undermine the basis of science as a whole. So,
Yes.
And just to comment on that, and then it would also be the question of when we read those articles that say that we are not deterministic, that we don't have any free will. Did they have any free will who wrote the articles? And if they don't, then why should we trust that it's true? It should be more of a metaphysical question, just like Polkinghorst said earlier about time.
no, I think that's absolutely correct. But that point, it's very logical to bounce the ball back to them with the statement, if you don't have free will, why should we take your statement seriously? That is not asked.
Should we stay on free will for a moment to swallow on it, or were you taking up into Okay, you had to say, yeah. Anything else on free will, just so we don't jump around too much?
I think one ought to keep in mind that there's always at least two kinds of explanations about everything that we do. And these scientific explanations are more of the nature of a description of a mechanism. But if I come into a room and see a kettle boiling, I can give you a scientific explanation of why it's boiling. But that's hardly relevant. I was wondering if somebody's making tea.
I still feel there should be one. And if everything else needs to be cancelled out, classical saying one doesn't exist, and quantum theory is saying one doesn't exist, then and they're also trying to be kind of complete, or at least nearly complete, as far as that's concerned. Yeah. Then where is it?
Well, okay, that's precisely the point. That if we make the statement that I would like to make, that there is that concepts or experiences that we have as consciousness and free will, that they are something that simply cannot be explained by physics. So that is that there is a substance or a phenomenon there that simply has to be added to the physical world, and that simply there's more than just a physical world. Well, in principle, I tend to believe that, but then I think if you want to avoid that they're completely two separated worlds that still seem to be strongly correlated, because when we take a decision and when we think, there are actions, there are activities in our brain, so and also when, there's also reason to believe that when our brain stops to function, also we lose our consciousness. So they do not live independently. So this suggests a dualistic view of the world that requires an explanation of its own. So I think it is not a solution just to say that we simply had to add phenomena or experiences to the physical description. But then I think the question how the relation is is rather urgent. And there, I don't think we have made much progress there yet. I have no clue.
Yes.
Yeah, although, as you perhaps know, I don't believe that fundamentally we have free will. I think God determines everything. I still think in the quantum thing, I suspect that if you followed in just one branch of what I believe to be ever many worlds, you would not be able to predict. It's only the determinism would be over the entire many worlds. Now, of course, we don't know, but I would suspect that a lot of the processes when we do mental thinking, and for example, you were thinking what to say, I would suspect that there are quantum uncertainties in that. And what came out in our world is perhaps different from what came out in a different world. And since
I'm talking in all those worlds.
yeah, so I wouldn't be at all surprised if you said different thing. You know, suppose we started, suppose we imagined focusing on the quantum state of the universe in which you had the conditions that we remember you were having at the beginning of the lecture. So of course there's lots of other branches, but let's ignore that for the moment because we'll assume they don't come back in here. So you just start with that and evolve it forward. Then I would highly suspect that the components of the wave function now have quite a bit of different things of what you said and what I wrote down. But I also suspect that there's big correlations, there's big entanglements between what you said and what I wrote down. So I'm a little, I mean, you had one statement about you didn't think quantum entanglements were important, but I suspect they really are really big entanglements. Of course, I would agree that they're entangled with a lot of things in the environment. It'd be very hard to identify two systems that are entangled with each other and not entangled with something else. I mean, in other words, it wouldn't be coherent entanglement.
I don't understand the term entanglement here. I would understand correlation, but that's not what you mean. Entanglement is something.
Well, I mean, what I mean is that the quantum state of the whole thing has one piece in which you said A, I heard A, and the environment also heard A. But it has another component of the wave function in which you said B, I heard B, and the environment also has a record of B. And then there may be more things. So in other words, it would be an entangled state. There would be, you know, for each component of this world, there would be, you know, a state for you and for me and for a whole lot of other subsystems, and then you take that in the wave function, then plus some term that's got a bunch of things for the other possibilities, and then plus. So it really is an entangled. It really is an entangled state.
This multi-world. You mean the various universes in the multi-universe?
Yeah. So if the wave function doesn't collapse, if we don't collapse the wave function, each time you say something, if we don't collapse the wave function, then of course I don't know at what extent quantum uncertainties get magnified into classical ones, but that quite often happens for chaotic systems, and of course I don't know whether our brain is chaotic, but since it often happens for chaotic, I wouldn't be at all surprised if it did happen, that what you said, I mean, of course a lot of it you had written down before, so probably given the quantum state you'd have your, you know, we have the handouts, you have it on the PowerPoint, so that probably didn't have much quantum fluctuations from what you said, but some of the particular phrasing that you said, I suspect came up at the spur of the moment because of quantum effects, and the particular words at which you said at certain points, I suspect, really are different in different components of the wave function. But in the component where you said one thing, we have this entanglement with it. I mean, we hear maybe almost the same thing. But then in the other component where you said something else, we have that. So that really is an entangled state. I mean, you might say it's correlated, but it's also entangled because it's different.
It's a superposition.
It's a superposition, right.
I experience only one.
Yeah. So of course we experience, we only remember one.
Also I mean, that is, if I gave a different talk in a different universe, and if I have no experience of that, what does that tell us? So that.
Well, yeah, it's true now. Of course, you only have the memory of this one part. I mean, of course, if the picture is true, there would be another component of the wave function in which you would have a different memory. And it's just, of course, I mean, I think essentially related to the second law of thermodynamics, that what we remember is fairly classical. We remember sort of a history that's fairly classical. We don't have a memory of these huge different numbers of things. And it's partly because the different possibilities sort of don't come together to interfere. They generally sort of separate out. But I mean, that's not an absolute thing, but it's sort of a general property from second law of thermodynamics that entanglement increases, in other words. And usually it rarely decreases. That's sort of anti-thermodynamic behavior that can happen, but it's, you know, somewhat rare when it happens.
Yeah, well, for me it doesn't explain much. But I mean, mean, logically, that could give a picture of what is going on well, say that if you use that also as the basis of our consciousness, then the multi-universe picture for explaining the consciousness, well, it does explain that there are many different possibilities and different options, different actions that I could have taken occur at the same time. But to use it as an explanation of my freedom of choice, I find it hardly convincing, I have to say. It may be a logical construct, but since it still contradicts my experience.
Well, no, it doesn't, because your experience would be, in this component, you would just have the experience of this. So there's no, it certainly doesn't contradict experience. It's just that you don't have a WYSIWYG view. What you see now is only your component. You have no direct evidence of the other parts that split off. So there's no contradiction. But I'll agree with you. It doesn't explain why you have to still connect the physical world to consciousness somehow. So by itself, it doesn't explain it.
If I understand you correctly, then this suggestion is in the bottom line that it is the quantum structure of the world that is also the basis of free will.
Well, I guess I'm saying it's the basis for the fact that I suspect we couldn't even in principle predict uniquely what we would do, because in actuality we would do different things in different components.
That means that the unpredictability of someone, that the indeterminacy of someone who still has a freedom of choice is a quantum indeterminacy.
Yeah, now of course I would not say it's really freedom of the will, because I'd say if you take the whole set is what occurs, and the whole set is deterministic. Yeah. So it's kind of a funny thing. You might say, well, do I have a free will to do A or B? Well, in this picture, you do both.
Sure.
But you're not ultimately free, because both do happen. But of course, when you in the branch where you did B, you could say, well, before I made the choice, I had nothing that enabled me to predict that I would do B. So it's unpredictable. But I wouldn't say it's really free will, because you do B in one component, you do A in the other component. So it's not free will, but it is, at the end, you couldn't say, well, I could have predicted that.
So maybe there's quite a few hands going up here. So just one facetious comment, just for light relief in the middle of this. I just had this wonderful vision. We have matching funds, for our institute, and I had this vision of an infinite number of Faraday courses going on in different multiverses, and the scope of generating matching funds out of the Templeton Foundation at this point is just immense. Sorry, I just had that amazing thought right in the middle of your conversation. So we'll reserve that for time. Yeah, Art.
I just want to jump back on something you mentioned. This is the quote from Roosevelt about the human observer and consciousness getting inside. I've never really understood that very well, for the following reason. It seems to me that when you look at wave function collapse, what is mysterious is why in a particular instance you get A or B. And I agree with you that it doesn't, that just saying that that's stochastic in some sense, that I can't predict it, doesn't solve any problems with consciousness, whether I go into many universes or not. But
the problem is that if you have this picture, say, of the interpretation of quantum measurement, then the question is, at what moment does the state adapt itself to the result of the measure?
Exactly.
That brings in the consciousness, at least in Roosevelt's argument.
So this was the question I'm trying to ask, which is, I don't understand why that's the case, because if I take a two-state quantum system and I couple it to some kind of heat bath, I can show in certain conditions you can have a phase transition. It'll collapse out one of the two components of the wave function. It's a classic kind of a decoherence argument. But it doesn't really matter whether I'm there watching it or whether I've got some instrument watching it, or I've got some instrument watching it. As long as I connect my quantum system to some larger system. Eventually, I get what comes effectively. I get some.
But decoherence is the same thing as that the system you're measuring on gets entangled to the outside world. First to the measurement system, and then it gets larger and larger. But always, at all times, you can describe that in principle by the state factor of the larger and larger system as entanglement. And decoherence simply means that your system got entangled to the outside world, and you do not observe the outside world, but only the system. So then you trace out the information that has gone to the outside world, and then you call it dissipation and decoherence. But it's, if you would have kept into account the whole outside world to where the correlation correlation has gone to, you would simply have an increasing and entangled state. That's still a state factor.
Yeah, I understand that, but I don't see why consciousness has any. Maybe it's also differently. Maybe I'm misunderstanding. Why does consciousness have a physical effect?
Historical context, but
maybe I misunderstood. But why does consciousness have, so maybe a simple thing would say why does
there is obviously evident. As soon as he, as observer, knows what the outcome was, then then you can say that is the end of the chain of increasing entanglement, for the simple reason that once I know it for a fact, it is a fact.
Well, some of the people who first advocated this actually thought the equations became non-linear. So it was still describable in physical terms. It was just that the quantum theory changed when you talked about consciousness. It's like Penrose thinks that quantum theory changes when you talk about large objects. It's a philosophy.
But for that to make in a physical sense, there has to be some non-linearity or something non-quantum mechanical that you're adding on, right?
Yeah.
That's what I'm saying. I don't really see.
Not necessarily non-quantum mechanical, but something they don't understand anyway.
Something additional.
Well, if you change the equations to become non-linear, you lose entanglement.
Anyway.
Yeah, but you don't have to have. Then again, you don't need an observer, right?
No.
That's the observer is somehow the non-linear.
Like I say, everyone watches things. It's large objects that do it, which are not necessarily conscious.
Yeah. Well, you can say you don't need the observer, but you at least you need someone to state what the final outcome is.
You could argue that that's just an approximation that they're making.
Yeah.
So if you look at the system long enough, I mean, even take something really simple as your double slit experiment, and you can destroy the coherence between them by putting a detector at one. Right? It doesn't really matter whether you're looking at a detector or not. It still destroys the coherence. That's a very trivial example.
Yeah, but then you take in the detector and you get back to the old story. That's what you say. Whereas what people like the Neumann were saying was something quite different. It's on Neumann who first did this. They felt the theory actually changed.
You could still erase this entanglement and then go back and restore the interference simply by so as long as there has been no observation. That is, I think, the way that Rosenfeld thought about it. That you can see the interference disappears, but the interference does if you have this entanglement with the measurement system that causes the disappearance of the interference. That can always be always up to the moment that the detection screen is collected, that you see all the points. You can always restore the interference simply by erasing this entanglement with the detection system. As long as you keep inside the domain of the quantum mechanical description of the whole process and keeping the state factor complete, nothing is lost.
I just understand why it has to be consciousness that is the thing that.
Well, okay. He said it is the observer. He doesn't really mention the observer is a person.
But isn't he really just saying, okay, if I decide at some point to make this thing classical, okay, whatever point I decide that, I call that point of decision the observer, right? And if I've got a system which is sufficiently entangled it'll look like a classical system.
You cannot make it.
That's not what the people meant. I mean, von Neumann talked about this couple all the time.
That's right, but
he quite definitely meant the theory was different from Wigner, who was another great person, propagated this idea. Quite clearly meant that he would change the theory itself. So there would be a theory which involved consciousness or something. I don't personally believe this, but that's what they say. Yeah,
but I don't think that's what Rosenfeld's saying.
No, I don't know why it's decided with Roosevelt actually. I mean,
well, it's
his idea.
It is Roosevelt brought in the human observer, and the fact that it is human, I understood it as a conscious being. It's more than an apparatus, and that was his conclusion of his interpretation, say, of the state of affairs, of how quantum mechanics work. That the reduction of the wave function, or the projection postulate, or whatever names have been invented for that, that chain of events ends as soon as we know, or I know, or he knows, what the measurement result is. That was his argument. And I agree with you that there are lots of things to say against that, but that it is different from what other people say. It's certainly different from what Bohr says.
I think we just got a little time left so in this session, so should we have this question? Yes?
Actually, it's just coming in on that. In the calculations, I think you mentioned at the beginning where you take, say, a spin a half and you couple it to a heat bath and you want to decohere. If, say, Hamiltonian has spin up having a slightly different energy than spin down, and those are the energy eigenstates.
Could you speak a little louder?
Sure. If you start with a Hamiltonian of a spin, which has got a high energy state spin up and a low energy state spin down, and you have initial conditions for that spin is in a 1 over root 2, 1 over root 2 superposition of those two states. And then you evolve the whole coupled quantum system. What you find is that it decoheres all right. You get a density matrix which has just got a halves along the diagonal and zeros elsewhere. So it's kind of classically like it's either up or down, but you still don't know which of those two cases it's going to take, and decoherence can't tell you that.
No, exactly. We agreed on that at the beginning. So that's the fundamental mystery, which is you don't know in advance which of the two is going to be, right? But I think that's different from what Rosenfeld is saying.